All right. So welcome everyone to the Demography Workshop. I'm from the Center for the Economics of Human Development, and thanks to Linda Waite and NORC and Center on Aging for inviting us to organize the workshop this quarter. As you see, we've still got a few more seminars lined up, and we hope you can join us for those as well. And some of the videos from the previous talks are on the website. And today we have Dr. Victor Ronda, who's a senior research associate at the University of Chicago's Department of Economics. He's also a research fellow at Trifigden Center for Child Research at Aarhus University. And he conducts research that explores how social and biological factors together influence skill formation during childhood and how skill disparities lead to socioeconomic inequalities later in life. And he's also the Associate Director for Research at CEHD. So he co-leads a lot of projects. And two of the recent papers he has are looking at the intergenerational effects of peri-preschool study following up at age 50, and then also work with three decades of records and samples from rhesus monkeys, and again looking at intergenerational early life disadvantage. And so you're most eager to hear from Victor, so Victor, over to you.
Thanks, Alison. Thanks for the introduction. Let me share my slides. Oops. Okay, so first of all, feel free to interrupt me if you have any questions. I don't know how many of you are familiar with the work on genetics. So if you do have any or find questions, feel free to jump in and mute yourself and ask questions. This work here is joined with Michael Hoslam, which is in the call, and Mikko Homark. And the idea of the paper is try to understand a little bit better how biological and social factors interact with informational skills, in particularly how genetics of the child and the parents influence the formation of skills. And this is something that we think it's new and it hasn't been done before, at least not in the same framework that we're doing. Before I go into the talk, I just want to clarify a little bit what we mean by genetics. So what we mean by genetics is the educational attainment polygenics course. So we're talking about genes that have been associated with education, or genetic markers, or genetic variation as being associated with education. There could be other genetic variation that we're not capturing here, so that's just something I want to say up front. And also, when I mention genetic variation, I mention genetic variation within a specific group in the UK. So they are all individuals from the same ancestry. They're all Europeans, and they all born in the same city. And a lot of the variation I'm going to be using in the paper is actually within a family. So it's whether the child inherits certain variants from her dad or her mom, and whether the child does not. So that's kind of the variation we're going to be thinking here, not across groups. Okay. So to motivate the paper, we start with this idea that individuals have different skills, have different abilities. I think we all agree that that's true. The work of CHD has shown that. We also know that these individual skills, they start very early in life. So even at age 1 or 2, we see very differences in skills and knowledge across children. And we know that this variation is actually very important. So it explains a lot of the variation we see in, say, education, earnings, marriage, fertility, criminality, and anything that we think that is relevant as a social outcome has been connected with these skills that are developed in childhood. I think most of us would agree that family resources are important, and not only family, but just environment in general is important at explaining the differences in skills. Maybe less people will be comfortable with the idea that genetics can also explain these early differences in skills. But that's something we're going to be showing and talking a little bit today. We're going to be arguing that a little bit of the discussion on genetic influences is a little bit misleading or wrong. Usually people think about genetics and these family resources as two independent components. And we're going to be showing that that's not true. Also, people tend to think about genetic influences as something that's static or deterministic. So that if you have certain genes, you're going to have certain outcomes, or the effect is fixed across the life cycle. We're going to show you that that's not true. In fact, we're going to show that genetic effects are actually dynamic. So they change across their life cycle, especially at early ages, and they depend on environmental channels. So they operate via parental investments. And because of that, they can be changing their social behavior. So genetic effects is not a constant, it actually depends on the environment through which the genes are operating. In particular, what we're going to be doing, we're going to be incorporating genes into a model of skill formation. So this traditional model of skill formation in economics, we're going to think about how would genetic markers enter such a model. And we're going to identify three main mechanisms. And these are both conceptually, but also empirically, we can distinguish between the three. So the three mechanisms are, well, the first one is what we call the direct effect of child genes on skill formation. And the direct effect is what most people would think of as the effect of genes, right? So some kids, some certain individuals, they're born with certain genetic markers which help with their brain development. And because of that, with the same level of stimuli, they might learn concepts at a faster or a slower rate, right? And this could be an effect initially on the initial skill of the child, but also an effect on the accumulation of skills could be faster or slower, depending on the genetics that the child inherits from parents. The other two mechanisms are new, or at least not as well established. The first one is what we call the nurture of nature. Is this idea that parental investments, when parents are making parental investments decisions, they might be thinking about the child's genetic makeup and making informed decisions based on that. In economics, you can think about the ideas from Becker, say, about reinforcing versus compensating investments in children. The new thing here is that we're thinking about compensating and reinforcing as a function of the genetics of the child, which are now observed and wasn't observed 30, 40, 50 years ago. And the last one is something that people don't discuss very much, but this idea that parental genes can also matter for skill formation. We call this the nature of nurture effect. Parental genes can matter in a variety of ways, including via parents' skills, education, and resources, family income. And because of that, parental genes can also influence children's skill formation. So we're going to be showing the three channels are important determinants, and we're going to quantify the relative importance of the three.
Victor, I have a question.
Yes. Yes.
Can you go back to the previous slide?
Yes. Sure. Yeah.
So for the nurture of nature, do you observe also if the effect is heterogeneous depending on parental income, for example, or parental background? In the sense, if, like, what is behind this effect of child genes on parental investments? Is it because they have, for example, low-income households have faced some financial constraints, and then they have to invest more in one child than another, and they choose the one that have better genes? Or, yeah.
So that's a good question. At the moment, we haven't looked actually at heterogeneity in the investment function. So we have some results where we rely the return to investments to be different across the child's genes. And there seems to be some positive interaction, but it's actually not well identified. But we haven't looked at the investment policy function as a different for different families. The way we're thinking of this is just more of like the model of preference. So some parents have a preference for reinforcing or compensating initial differences in skills. But we haven't looked at heterogeneity on that. We should. Thanks. When we get to the function, you can see exactly how we do it.
Could I also ask a question about this slide?
Sure.
I was wondering whether this investment by parents in their children and how this depends also on their genes. I was wondering if I could look at this as intergenerational wealth accumulation as well. Is there some mechanism you think that can start way back with grandparents who invested a lot and this accumulates to the child's life? The family.
I don't know if that's where you're getting to, but it's an important point that when we talk about genetic effects from the child, these are well identified, because we're talking a little bit, we're going to be using variation in the variance inherited by the child from the parents, and that's completely random, it's given by nature. So we can identify the child genetic effects, but the effect from parental genes actually capture both the both parents' genes, but also from grandparents and other family members, which also have the genetics correlated to the parent. So it's not really an effect of the parental genes, it's the effect of everything that is genetic associated with parental genes. I don't know if I'm explaining very well.
Yeah, that's clear. Thanks.
Okay, so what we're going to be showing is that once we do this exercise, there's a few important takeaways. First, genetic influences are dynamic and increase at children age. So we're going to see the effect of genes actually increasing instead of decreasing. So when I first thought about this idea, I originally thought that you're born with certain genes that affects your stochastic skill at period 1, and then genetic effects would decay across the life cycle, right? But it's actually the opposite. You're born with certain genetic endowments, and the genetic endowment is going to help you accumulate skills at a faster pace. So there's this idea of the direct genetic effects accumulate. And also in our sample, at least, we see that parents tend to reinforce initial differences in skills. So because of that, they're also going to reinforce initial genetic effects, which also tend to increase over time. Both of these are going to be important to explain why we see the effect of genes increasing over time. And the second thing is, because we see that genetic effects occur via parental investment, we can argue that genetic influences are actually not fixed or determined. They actually can be changed via change in social behavior. So if you think about policies that equalize investments across children, they're actually going to counteract a lot of the genetic effects and decrease genetic influences overall. We show that with a simple simulation. Okay, so let me get into the genetic background first and explain to you like how we think about genes, what genes are. I know people have different knowledge about biology from high school and before that, and then explain how we are measuring genes from children, how we can observe that. So to start, the human genome, we have about 3 billion genetic addresses in our DNA. So our DNA is the string of letters A, T, G, or C, and there's about 3 billion locations that we have. What is interesting is that among these 3 billion genetic addresses, about 99% of those addresses, they are the same across everybody in the world. So everybody in this call will have the same variants A, say, or G or C in 99% of those locations. But there are some variations. So 1% of 3 billion is still a lot, right? And this variation is what makes us individually different. There's different types of genetic variation. The most common one, and that's what is used by most researchers, is what's called SNPs. SNPs are single nucleotide polymorphisms, so they're just variation at one specific location in the genome. So in a specific location, some people might have an A adenine, some people might have a T thymine nucleotide pair there. And in humans, there are about 3 million to 10 million of those SNPs, depending on how you count them. And the interesting thing is that the vast majority of them, almost all of them, are biallelic, meaning that there's only 2 values that you can see in that genetic location. So we can think about the genes of an individual as a vector of SNPs, where for each SNP we have a value 0, 1, or 2. 2 meaning you have 2 A's, 1 you have an A and a T, for example, and 0 you have 2 T's, right? And the way to think about it is easy to see graphically here. So here I have an example of a family genetic data. And you can see that the DNA is like a long string like this, where you have, for example, C and C, T and T for the mom. And these are just locations in the genome that we see variation. So the vast majority of the DNA, these letters are the same for everybody. In some locations, and they're sparsed across the genome, there's some variation. And we can count those. For example, suppose we assign a value of 1 to a C, then the mother will get a 2 at this location. The father has A, so he gets a 0. And the child inherited C from the mom and an A from dad, so the child's gonna have a 1. So you can think about genetics as like this vector of 0, 1s, and 2s, which really simplifies the problem for us researchers. The important thing here, and that's what I'm going to be exploring in the paper, is that we know the process of inheritance from parents to children. So for example, here, for each variant, the child from G and C, there's a 50% chance the child's going to inherit a G, and a 50% chance the child's going to inherit a C from the mother. And that deterministic is completely random. So the determination is random by nature. We can exploit that to actually capture causally the effect of the child genes on outcomes. So we know, for example, that in expectation, the child is going to have the allocation about 50%, 0.5 of the variation of the father, 0.5 of the mom, but the difference between the realized inheritance and the expectation is random by nature and exogenous to any environmental effects that are realized before conception. After conception, they can be influenced by the child's genetic makeup, as we're going to be showing later on. Okay. So basically, genetic endowments are multidimensional. They comprise millions of individual variants. They are determined by parental genetic pool and correlated with parental genetic endowments. But the variation in child endowments, conditional parents, it's random by nature. So these are all the 3 important points I want you to remember. So how do we use this? So we cannot use like a million variants, right? There's nothing we can do with that. So the way researchers tend to use those variants, summarize them into one unique score. So we'll call this a polygenic score. So polygenic score is a weighted linear combination of the 0, 1, 2 SNPs, where these weights, these betas here, they come from a large association study that is done outside our analysis. So individuals that are not included in our analysis. And these betas, they're computed by regressing the outcome of interest, the years of education, on each of these genetic variants individually to get these coefficients of association. And people have done that using millions of individuals in the outside sample. And so we get those betas, and then we compute the score for the individuals in our sample. So this is what's called polygenic score. So you can think about here, the polygenic score is just multiplying those 2, 0s, and 1s by some weights, and then you end up with like a score. And the important thing is there's a lot of variation in the score from mothers, parents, and specifically children. So it could be that the child has a lower score than the sum of the parents. So in this case, 1.4 versus 1.8, 1.7, or it could be that the child has a higher score. I'm going to show you how the distribution looks like. So this is how we think about genetics. Let me talk about the data specifically, what information we have. So the data we're going to be using for the estimation of the model, and it's called the Avon Longitudinal Study of Parents and Children, ALSPAC. This is a British cohort of about 15,000 children born in 1991-92 in Avon, England. That's what I was saying, that the variation we're looking is a very homogeneous group of individuals. And what is important about this data is that we have information on 3 main things. So we have information on children's skill development from age 0 to age 7. We have information of parental investments. So this is about children activities with the parents, children resources, whether the child has a book or not, and interactions, and genetic information on both children and both her parents. And this is what is key, and it's hard to find. It's hard to find a data set with the trios. And the problem is if you don't have the trios, you don't have the child, which is common most data sets, is that whatever effect you get from the child polygenic score could be capturing influences from the parents. Doesn't have this causal interpretation that we're going to have. But because of the genetic information is not collected for everybody, we have our final analysis only includes 1,200 children. We're working on robustness right now. I'm going to show you some preliminary results where we impute parental genotypes, paternal genotypes, and we can do that using different methods in the literature. And once we do that, we increase our sample size by significantly to about 4,000 children. And let me just show you a little bit of the sample selection so you understand how it looks like and what the problem is. So the problem is like for the full aspect, we have 15,000, and the information genetic endowments is only 8,000. But if you look at the biggest drop here is information with paternal genetic endowments, only 1,400 out of 6,000 individuals have information on the paternal genes. And we believe the reason for that is that the father has to be present at the home for their DNA to be collected. And especially at divorced families and families where the biological dad, does not live with the child, this information was not collected. So just so you look here, I'm looking at so this is just summary statistics for the reduced sample and the individuals that we dropped because of lack of paternal genes. And you can see that the PGS, which I'm going to describe what it is in a little bit, is like the genetic propensity for education for the child is much higher in the individuals that we do observe paternal genes. So imputation, we're going to help us with that problem, increasing sample size, but also bringing back us to a sample that is more, which is more representative of the whole population in England. Okay. So the measurable skills we have are collected every 6 months until the child turns age 7. They're reported by the primary caregiver, which is usually the mother. And here we focus mainly on cognitive skill development of the child. And to measure the cognitive skill development, we're going to be looking at development milestones for different child ages. So for example, at age 2 to 4, we have a variable about combine 2 different words. And age 4 to 7, a variable about can the child read a story more than 10 words per page. You can see here that we have many different milestones, and they're collected at different ages. But importantly, as I'm going to mention a little bit, we have some repeated measures across different ages. And this is going to allow us to identify the limiting factor model to control for measurement error in children's skills and to track the evolution of skills over time. For parental investments, we're going to be using a series of questions about parents-child interactions. For example, the frequency the mom reads the child or the partner shows child picture books. We're going to capture parental activities and child access to resources, for example, number of books owned by the child. And again, this is collected every 6 months until the child turns age 7.
Can I ask a question?
Yes, please.
Can you tell us a bit about the socioeconomic backgrounds of these parents? In particular, what I have in mind is following up on Mark's question with like a Becker and Tom's 1986 type of paper. Do these parents get to afford to invest as they please on these children, or are they like liquidity constrained or credit constrained and they have a hard time investing as they please?
Yeah, so two responses. So yeah, that's a good point. Like I said, we haven't looked at variation in responses across parents. A lot of you can see the measures of parent investments are actually activities. So it's like more of time investments than resource investments. So if you look at the list of measurements we have, is the frequency the child goes to places of interest, to a library, frequency the mom reads the child, the partner sings the child. So education plays a big role here, but there's no reason why the parents cannot do this. It's not like about they're constrained, right? So they cannot read to the child every day. It's just it's more of a choice. We also, we could look also at parental income. We don't have very good measures of family income in the data set, so that's one constraint that we have. But we should look at heterogeneity. That's actually a good idea. Okay.
Victor, I have another question.
Yeah.
And do you observe if parents enroll children in extracurricular activities, or do you observe that in the data?
I think so.
Okay.
I don't think we have used that, right? It's not here.
For example, if they enroll into play an instrument or sports.
So we do. Can you see the frequency goes to special classes and clubs, called special groups. So all these different things are measures of interaction of parental investments. So our measure kind of captures this. It's one single measure. We haven't looked at multiple measures yet, but it's one single measure that captures all these different dimensions of parental investments in children, and they all relate to each other. So this is capturing like one factor. But we can look at more specific measures. We haven't done that yet. Do you have a story in mind?
Oh no, I was just wondering if that was also observed in the data, because I mean, I would assume that that if children also go to extracurricular activities, then that could also be an additional. It can also have a positive impact for later on human capital or income, right? But yeah, just wondering. Thank you.
Yeah, so it's part of the income of the investment measure. So it's a catch-all. I mean, that's kind of common literature to do that, and we don't have we don't have more detail on like actual time investments or actual monetary investment with children. I wish we had that, but we don't. Okay, another thing I wanted to mention is this idea. So we're going to be, I mentioned that it's important to have parental genes and child genes, right, in the analysis. And this kind of highlights a little bit the variation we're going to be using to capture genetic effects. So here I'm plotting the distribution of the child EAPGS, the Education Attainment Polygenic Score, which captures the child's genetic propensity for education. And this is being normalized to be 0 and 1 in our main sample. And we're plotting as a function of the parental decile on this EAPGS. This is the sum of the moment. That's, again, PGS but normalized. And you can see that for each being, there's a lot of variation in the genes. So it could be that for parents with really high genetic propensity for education, the child is unlucky, if you want to call it that, and it has a very low propensity for education. Or it could be, again, families where the parents have very low genetic propensity for education, the child could be very lucky and inherit all the positive variants. So there's a lot of variation across groups here. And we're going to be using that to identify the genetic effects of children genes on a variety of cognitive skills. Okay, so is there any questions on the PGS that everybody understands? Okay, so the empirical model, our main model, main estimation model, is actually going to be very simple. It's going to have three main components. So we're going to have the child initial skill endowment function. So it's going to determine the initial skill endowment of the children at age 0 to 2. Then we're going to have a technology of skill formation, which is going to describe how the skills evolve across time. And then the investment policy function, which describes how parental investment decisions are determined. The child initial skill endowments are going to depend mainly on the child genetics, the child PGS, and the parental PGS. So here we're going to be thinking about both parents together. I can show you some results later where we decompose the two. And it's going to be a function of individual controls. And for our main specification, we're going to be thinking of controls as very basic set of controls, so basically gender and birth order. And the reason is that, especially if you want to understand the effect of parental genes on a variety of outcomes, we cannot include things through which the parental genes influence children's skill development. So if you control, for example, for maternal parental education here, that would be one of the channels through which parental genes influence skills. So our axes are going to be completely variables that are not genetic determined. For example, gender.
Victor, do you have a control about residence, place of residence, like to capture network effects and such?
So they're all born in the same. They still live in the same area, at least at these early ages. We haven't looked at whether people migrated, but my understanding is that very few migrated. So they're all born in the same city, Avon, in England.
But can you hear me?
Yes.
So do you have any initial measure of the children's health condition, at least the birth weight, something like that? height, birth height.
We should have that.
Uh,
You're thinking that that's
Yeah,
endowment?
especially like for the initial skill set, that could affect a lot, like in terms of the initial skill endowment, in terms of the health condition.
Yeah. So we're thinking of these measures at age 0 to 2. So this is more related to age 1 and 2 than age 0. So it's whether the child focuses eye on small objects or can build a tower of bricks. That's more on the age 2 side. Or plays peekaboo with their mom, is responsive to parental interactions, right? So these are the very basic measures. We play with this a little bit, and there wasn't. Our results didn't depend on that very much.
From my understanding, like in terms of the initial skills, like the health conditions, you mean what you find like the measures that not affect the outcomes of the 0 to age 2 performance is what you want to.
It's including additional measures of health in this set didn't change the results in any significant way. That's what I'm saying.
I see.
We could have just used health, but we're focusing
that will be to see whether your sample include a lot of disadvantaged families. Yeah, if it include a lot, I would suggest including the health measure, because that will help you to identify some kind of abnormal children. Like if they, yeah, that will be very helpful, like measures to help you to indicate that low birth weight is really different from the children with the normal birth weight. Yeah.
Yeah, we can look at that. I mean, there's always this question about whether, low birth weight is influenced more for the. So it'll be interesting to see how it changes. Especially, I'm going to show you that.
Yeah, sure.
The difference between genetic effects from the child and the parents.
Yeah,
so maybe for
actually,
the health effects will be different.
Sure. I'm quite interested in like to see how the birth weight correlated with the initial genetic component. Yeah.
Okay.
Victor.
Yeah.
So the PGS is something that is it's like the sum of the betas, right? Something like that, and that's calibrated from a regression from another study, which was looking at education as the outcome, right?
Yes.
And now you're using this variable with sort of to explain a different thing, which is the skill, right?
Yeah.
And so, like, how do you deal with that? And also there's like, these are estimated betas. So this is like a PGS hat, or like an estimate, right? So does that uncertainty kind of propagates through your model?
Yes. So they're both very good questions and they're very important questions. So the first one, it's so the answer is that that's the best we can do at the moment, because the EAPGS has been shown to be the most predictive polygenic score for a variety of outcomes, including cognitive skill development. So that's why we're using it. But it really leads to a problem in terms of conclusion, because all we can say is that the genetic variants that are related to educational attainment and weighted in this specific way, this is what the effects that we see, right? It could be that if we have looked at different genetic variances, the effects would look very different. So completely right on that. So the interpretation of results lies on the interpretation of genetic effects from variants that are related to educational attainment. I don't know if that answers your question, but that's kind of the first one. The second one is about measurement error, and that's a big issue that the literature hasn't solved. We're working on that in the revisions right now. So the second issue is about is that this PGS here is misestimated, because these betas are not perfectly estimated. In fact, we know that these betas have been computed in like waves. So the first wave is called the EA1, only included 100,000 individuals in the discovery sample. So to compute these beta hats, they only have 100 individuals. And then you see that this PGS explains about 1 to 2% of the variation in educational attainment in other samples. Then we did the analysis of 300,000 individuals, and it would explain about 3%. and then they redid the analysis with 500,000, it went to 6%, and the latest one, which is the one we use here, they included over 1 million individuals in the genome-wide association study. And because of the accuracy of these betas increase when you include more individuals, then the PGS effect also increases. So measurement error it's a big issue here, sure. So all the genetic effects I'm going to be showing you are both, one, dependent on the measure we use, so they're related to genetic effects from variants related to educational attainment, and two, they're attenuated because of the measurement error.
And sorry, last question on this, is it like, are these regressions sort of avoiding overfit in somehow? Because you still have like 10 million SNPs you're saying, and even with 1 million people. So how do they kind of do that? So
did they avoid overfit because so you're talking about the GWAS, or you're talking about my own?
Not your own, the external ones, these betas, are they able to sort of avoid overfit?
Yeah, so they do what? So there's I mean, we can spend more time talking about it after the talk if you want, but the way they do it is they do one regression at a time. So they compute one beta at a time. So they regress years of education on genetic variant 1, and then years of education on genetic variant 2. They do separate regressions. And then they account for the correlation among the different genetic variants to correct for the overfitting. I guess that's what you're calling it. It's like, but in practice, in the end, we don't know which variants are causal. All we know is that this specific location in the genome has a strong signal for educational attainment, or has a strong signal for Alzheimer, or has a strong signal for whatever health, whatever outcome you're interested. But we don't know what is the causal variant, and we don't know what's the causal pathway. That's something that people are working on right now. But what I can tell you is that once you do this analysis and you get these polygenic scores, they're highly predictive of the things that you're trying to predict.
Thank you.
Does that answer? Yeah. Another issue.
Can I ask a
talk to?
question?
Yeah, go ahead. Sorry.
So, I mean, so these weights in principle might pick up the impact of investment and the interaction between genes and parental investment, etc., right? So isn't it a problem later if you want to learn about these interactions, but these waves implicitly are picking up those interactions, right? If there is any reinforcement, for example, by parental investment environment.
Yeah, that's great. I mean, you guys are getting to this is the frontier of the research in genetics and social science. So basically, there's two issues that you referred to as well, which are very important. So the first issue is that once you do this GWAS, these betas, they're capturing both direct and indirect effects. So they capture the effects of the genetic variants of the child on the education of the child, but they also, because we're not controlling for parental genes in those analyses, they're also picking up effects via parental investments. So there's some work, I've been involved in that, trying to do what's called within family analysis. So we look at variations in sibling genetics and look at how that predicts variation in the education of siblings. So that would only pick up the direct channel. But this is still like ongoing, but the results haven't been published yet. And the second thing is that when people do the GWAS, basically you're getting signals from variants that have an effect on average across the population, right? So if you're particularly interested in G by E, so for example, whether the genetic effects are higher for certain groups versus other groups, the polygenic scores do not capture that. So that's another issue with the analysis of the polygenic scores. I think you're asking mostly about the first, but the second one is also important. So all I can say is that these are kind of like in frontier of the research, and this paper only partially address some of this. Okay, so let me get to the model quickly. So the model is very simple. We have a few different versions. They all give qualitative similar results. So that's why we kept the simplest one. So the model contains three main components: the childhood issue skills, technology skill production, investment, policy function. So the skill production, or the initial skills already mentioned. We're trying to see how the initial skills are a function of the genetics of the child and the parent. The technology of skill production tells how the skills evolve over time. So skills at period T+1 are going to be a function of skills at period T, a function of parental investments. And this is what's traditional literature. And then we are including the child's genetic score, the PGS of the child, and the PGS of the parent. We also have a translog version, which takes into account interactions between different inputs. The results I'm going to show you, the main takeaways do not change when we do that. But we can talk about when we get to there. So that's why I'm saying this is the Cobb dogma as a simple specification. The investment policy function is also going to be log linear. The key thing is that the investment in period T is going to be a function of child skills in period T, which is again traditional literature. But we are going to allow now the child's genes and the parental genes to also influence parental investment. So that's kind of the
So in terms of, do you impose the same normalization as what Aligoplay and Wistful what they did, or do you use different way?
So we're going to estimate using the Agostinelli and Wismol algorithm. And the key thing that they have is that we need some aging variant measures, right?
Yeah.
And we do have aging variant measures for the investments. I mean, there's always this discussion about what is an aging variant measure, that do they really exist? So we're imposing the restriction that we have an aging variant measure for investments, and for skills, we're going to have multiple aging variant measures. So we're going to allow for the transition. Let me describe it to you. So for example, here, can the child build total 8 bricks? So this is going to be aging variant for these 3 periods. And then, for example, plays cards or board games. I'm going to be aging variant for this remaining periods. So that's kind of the assumption allows us to track the evolution of skills across time. We also use different aging variant measures. For example, you can use this for this period, this for this period, this for these 2 periods, and this for these 2 periods, for example. And the results are, again, very similar once we do that. I don't have it here to show you, but the method requires you to have these age invariant transitions. So the factor loadings are the same for both periods, basically. That's the sort of assumption. Does that explain your question?
Okay, yeah. I'm thinking whether you can do some kind of test to see whether those measures are age invariance measure, but we can talk about that later, because
yeah, that would be great.
Yeah,
since the how to do that.
I mean, the paper like we read with Professor Heckman is basically talk about, you know, what kind of like assumption impose and how to examine like age invariance or like a scale invariance like across different measures, and we can identify those. Yeah, but that's fine. Like we can move on. Go ahead.
Yeah, that'd be great. I mean, like I said, the key thing in this paper is just inclusion of this variance, right? But it'd be good if we're doing this carefully. And the invariance policy function, again, it's going to be log linear. Again, this is the new component. So we can think about mechanisms in the simple model. Allows us to think about these 3 different mechanisms.
Can I ask something?
The direct effect. Yes.
Can you hear? Sorry, I'm actually hiding here. I'm hello. I was hiding the whole time. Hello. Can I ask about the investment policy that you have there? So can you explain something about? I mean, is this coming from some optimization problem, or is it? What's the logic that drives this investment policy that you have here?
Yeah. So you're asking like, why is it linear? Where it's coming from? Right?
Yeah. Or is there any?
So this is an approximation to it. It's an approximation to the investment function. So we know that the investment function should be a function of children's skills. That's the Eckman-Thomp's framework, and should be and we're allowing to be a function of the genes. How would that come about in the structural model? We had some discussions in the past, and there's some ideas, but the problem is that we do not observe a lot of things that will go into the parent investment decision to estimate a more structural model. So this is like a reduced form approximation to that this decision of the parent.
Yes, so essentially this is a reduced form approximation to something that, and you don't necessarily have in mind whether these gammas are positive or negative even, right?
No.
You just kind of let the data tell you what is going on there.
So that's part of so that's key actually. So we're interested in knowing whether these gammas are positive or negative, and this is the nurture of nature mechanism. It's about whether parents reinforce or compensate each different skills, and this is going to be important for genetic effects. If I show you right at the end, I'm going to show you that if you set this parameters to 0, or if you set investment to be the same for all individuals, genetic effects will change. Right, that's a key implication from the paper.
So can you give us a peek into the results? Are these gammas positive or negative? I mean, what do you get?
They're positive. So in this sample, parents reinforce. So both
reinforce the endowments.
Okay.
So in your mind, like the model will be, firstly, the genetic component will affect the initial skill endowment. That's true, right? That's the first equation. And also you think like the parents can observe like sort of things about the genetic part. And also the parents knows the children's skill development outcomes, and their investment decision will based on both the children's current skill performance and the genetic component. That's the story in your mind, right?
Exactly, yeah.
So, and also the impact of the parent investment, because here is a little bit tricky, since like the genetic part will also affect the skill accumulation function. So in your model setting, let me see, how do you think about what's the dynamic impact across period, like since it will affect the skill accumulation process, and also for each period it will have some kind of constant impact to affect the skill part. And just say if like all the delta 3 and the delta 4 will be positive, do you think like your model will report the genetic component will accumulate play some kind of dominant role, like in terms of the skill improvement or skill development for the children?
So I'll show you. So I think where you're getting into exactly the type of exercises that we do later on. So we can use the model, that's the reason it's been a model to simulate the path of skill growth for children with different genetics, and we can see if we close some of these channels, how would the effect change. So we can decompose the overall genetic effect. You can see like how much the variability in skill at different ages can be attributed to the genetics, and how much of the different mechanisms explain the influence of genetics across different time periods.
But you do not add in the interaction term, right? For example, the skill and the investment.
So we have some results where we do that. They're actually insignificant. I can show you in a little bit. The main message, that the results I'm going to show you later on, the simulations, they're very similar. So that's why we focus on the simple one.
Yeah, so the story about nurture, I don't know whether you want to try another kind of model specification, say the genetic only affect the initial endowment and that's it. And then like the parents' investment will be only the function of like they can observe the children's skill development, and then they will provide the the skill.
So we're testing this, right?
Okay.
So that's part of the test. I mean, if that's true, then this should be 0, right?
Yeah.
And it's I'm going to show it's not, but oh sorry, this should be 0. I'm going to show it's not. So let me get into the results, because I guess a lot of the questions are getting to that.
So, Victor, I have a question.
Okay, let me just show you So this is the results for the parameters, and then I can show you when I use a translog, when you put parental genotypes, so the standard errors they shrink, or the confidence intervals shrink, and also compare maternal with paternal. But Just to explain, we find that the direct effects are significant. So children PGS both influence the initial skills and the accumulation of skills. Parental genetics also seems to influence the accumulation of skills, but also parental investment. And we see that parents tend to reinforce initial differences of skills, both on the skills that are observed, but also on genetics. And when we impute the parental genotypes, so we increase the sample size that we have, these become, for example, significant. So you can see that the parameters change, but also the standard errors, the confidence intervals shrink. But these are preliminary. We're just on this. Okay, no questions.
And Victor, and here investment captures both parental time and parental money, both of them, right?
It's mostly time, but yes, it's both. We have, for example, number of books you have in the household, but it's more about interaction in terms of activities and experiences.
You see,
But
Victor, like in terms of the investment parameters, like for children's genetic, that's not significant. And for the parents, since the genetic component of the parents could be correlated with the education outcomes, right? So I don't know what's this parameter capture about, because we have that, we all know the higher education parents will invest more to the children. So if that part is the correlation, is not really the genetic part. Yeah, I'm not sure like the coefficient of the PGS from parents is really capture the genetic component part from parents. Yeah.
I mean, it is, right? I mean, so it's what I say, it's capturing genetic component from the family. So families where they have this higher EAPGS, they tend to invest more on children. The question is why? So the association has I cannot say it's causal because I don't have, if I had a grandparent's genes, then I could say it's causal, but I don't. So it has to be something about the family genetics. But there is this effect on investments. The question is why it has an effect on investments, and the answer is education. So
is it possible like you also conditional education is sort of say, oh, conditional education whether genetic will play some role here?
It is zero. Yeah. So this doesn't change. But this go close to zero. The blue one.
I see. So that means it seems is exactly what we discussed. Like the correlation is mainly come from the education levels from the parents.
Yep.
Okay.
Which is in turn genetically determined by the genes of the parent, right? So it's not like that we're not picking up a through effect here. We're just picking up an effect that it's mediated via education with the parents. That's something we're actually working on and trying to show what are the mediating channels of this effect.
Mm-hmm.
And I already play with this, and I know the answer. The answer is education.
Yeah. The reason is like why I bring it up, because that is exactly like what you said. What kind of policy like will be implemented, right? So if the policy is really like just genetic and we cannot change it because we cannot add it genetic, the gene for everyone, but like if the channel is like what you said is education, that would be a different story. That means like improve the parents' education level could help a lot. Yeah.
Yeah, but even if it is just genetic, it depends on where it comes from. That's a little bit what we're trying to say here. If it is a direct channel, then this is hard to counter. Policies is something that is biological and we can compensate, but we cannot change the effect. But if it's operating via how parents invest in children, so this reinforcing channel, then is due to social behavior. So if we break or decrease the influence of parents by equalizing investments, or parents have different policy functions, parents were having a compensating investment behavior instead of reinforcing ones, then genetic effects will change. So this part is changeable by policy. This part can be compensated by policy, and that's kind of the important distinction that we were trying to make in the paper. I don't know if that's clear or not, but that was the idea.
Mm-hmm. Oh, the other way we can say, because the next question, the equation is the investment is a very important channel. If parents could not invest more and the government also play the role, like increase the investment of IT. So that's another way they can improve the children's skill development. Yeah.
Yeah. So that's kind of picking up. So that's what I'm trying to say is like the investment could be changed as a function of genes. In fact, I'm going to be showing a little bit, if I equalize this to be the same across everybody, the overall genetic influences actually go down significantly because of these two parameters. And that doesn't have to be true everywhere. This is true in this sample. But if maybe if you look at a different in Scandinavia, maybe, we don't know, the pattern might be very different, or even the US, or like Mark mentioned in the beginning, it could be different for high and low SCS families. That's something we haven't explored. And the reason, just to explain why we haven't explored, is that because we had this smaller sample of 1,000 individuals, so and you can see the parameters are barely significant. So we didn't explore many heterogeneity effects, but now that we have the imputed sample, we can do more on that, and we should do more on heterogeneity.
Okay.
Victor, should we ask you questions, or do you want to kind of like drive to the
end?
No,
go ahead. Please ask questions.
So I guess I don't fully understand what you mean by what could be influenced by policy and like that, in the sense that you have just an equation for what the investment is, and that within the model, it's not a choice variable of anyone. So what do you mean it could be influenced by policy in some implicit way that is not specified in this model here? Or that's what you mean, that maybe we can give incentives to parents to invest in their kids, and maybe that's how we could manipulate that element, right?
I think Victor just want to estimate the skill production function, like with considering the genetic component here. I mean, if you think about here is the structural estimation of the skill production function. And I mean, think about that's a firm, right? Like put the labor capitals and then like have the output. And here it's just you try to estimate what's that parameters and change whatever direction, like the investment or like, the skill input and how to change like the next period, like the skill output. Yeah, that's what he wants to do for this table.
Yeah, and the idea is that this is changeable in policy. We don't have a policy. If we had a policy, this would be great, because then we can look at how this is changed by policy.
It's not quite a policy, but it kind of like plots something about how sensitive ultimately the achievement would be to something that could be subject to policy manipulation. Right?
Exactly. And I'm going to share some simulations for that, but again, it's just simulations without a real policy.
Yeah.
Okay. Yeah. So how do? Sorry. Oops. So this is the estimated effects. We talked a little about what we find. The problem, as everybody knows, is familiar with the literature, knows that you cannot just see this effects and understand how large or small they are. It depends on the variance of the shocks and skills. So we can do simulations to kind of understand this a little bit better. So here's just a simulated skill development from age 0 to age 7 for children with different PGS quintiles. So you can see in blue here. So first of all, skills increase over time, which is what we know actually happens in real life. But the development process is different for children with different educational attainment progeny scores. So in particular, children that are born in the lowest PGS quintile, they tend to be a lower development, and the development tend to stay low throughout the life cycle. And children at the highest PGS quintile, the higher genetic propensity for education, that's how I call it that, tend to be above, and this difference start early and then just accumulate over time. Another way to see this is to think about we standardize the skill at each year. So we think about the standard deviation of effect instead of all raw effects. And it looks like this. So basically at the very early life, the first period, the difference between children at the top and the bottom quintile of this educational attainment polygenic score, the difference between the two is about 0.3 of a standard deviation. But these differences tend to increase over time reaching at age 6 to 7 about 0.7 or 8 of a standard deviation difference between the top and the bottom of the distribution. So that kind of puts in perspective a little bit the effects that we're seeing from the EAPGS. And like I said, there's two things here. One is that there could be other genetic effects that we're not capturing because we're using the specific score. And two, even using the specific score, we know it's attenuated because of measurement error. And that's something that we're working on how to address. Another way to see this is to plot, to compute heritability. So that's kind of a common measure in these genetic studies. And when we talk about heritability, we're talking about how much of the variance of a trait, in this case, skills and investments, in a given period can be explained by variation in genes, right? And here we're talking about variation in this EAPGS. So you can see that the heritability of skills at different ages change across the life cycle. And particularly, the heritability tends to increase over time. So the factor genes are kind of dynamic. So very early in life, child genes only explains about 4% of the variation in skills, but later on, it's about 7%. And here you can see how genes also seem to explain parental investments, and that's kind of something that both of these things are new, in the sense that genes have the factor genes change across time, and that the factor genes operate via parental investments, or at least the parental investments are partially related to parental and child genes. And then we can do the mechanism decomposition, so we can try to think about these three mechanisms that we have. What is the relative importance of the three, and does that change over time? And I think, Jim, you asked about this. And here, let me just go to the table again because it's easier to see. You can see that these mechanisms have different importance across different periods. But if we focus on the last period that we have here, we can see that the three of them seem to be very important. So about 50% of the association between genes and skills at age 7 comes from this nature of nurture mechanism from parental genes. So about 50% of the association between genes and skills at age 7 are due to parental genetic influences. So this is important for the literature, each part of the literature that does not control for parental genes. So you can see that they're picking up a lot of environmental effects in genetics. But even when we look at the causal, or like the effect via the child's genes, once we control for parental genes, about 80% seems to be direct via the accumulation of skills, and about 20% is via this reinforcing mechanism. So parents investing more in the high skilled and high genetic EAPGS children. And you can see that parental investments are also determined half by parental genes and half by the child genes. Any questions here? Okay, so I hope this clarifies a little bit of the exercises and why we're thinking of doing these exercises. And then we can discuss a little bit the simulations that we're seeing. The whole idea is that because genetic effects operate via this parental investments channel, the genetic effects are actually not fixed. It's not like we can say that genes explain 10% of skills. We can say they do in the specific sample, the specific parental behaviors. But if we change how parents invest in the children, or if we change, if we provide everybody, for example, with access to health services, access to early childhood education, or home visiting programs that we'll be seeing in the other workshops, then we're changing how investments are allocated across children, and that would have influenced also how genetic effects influence children. So the effect of genes actually highly dependent on this investments channel. To make that clear, what we do is that we simulate the model, now assuming that everybody invests the same, all parents invest the same in their children. So we're breaking both the association between parental genes and investment, but more importantly, the association between child's genes and parental investments. So here in blue, we have the association between the percentile of the child's EA polygenic score and the standardized investment at age 5 to 6, sorry. And you can see that there's like this strong positive relationship between the two. So children with the highest polygenic scores, they also receive the higher levels of investments. And basically the equal investments policy, the simulation that we're doing, kind of breaks this association. And here you can see how that influences the relationship between the polygenic score and the skills at age 6 to 7. So the blue line again is the raw association. You can see that children with higher polygenic scores tend to have higher skills, standardized. But once we change how investments are allocated for children, this association changes. So it becomes a lot flatter, right? And you can see that the children that benefit the most are the ones with the lowest levels of the polygenic score, because they're the ones receiving the lower levels of investment. So we're just moving it up a lot for them. And for kids here, there's basically no change. And when we talk about heritability, we can see that the heritability decreases significantly from one to the other. So here we have the genes explain about 7% of the variation, 7.5% of the variation still at age 6 to 7. But if everybody invested the same across children, it was go down to 4.5. And like we said at the beginning, it's unclear whether in all societies or in all groups, parents actually reinforce initial differences skills, or if they compensate. If they're compensating, these numbers will fall even lower. So it just puts the idea of go ahead.
Okay, sorry. So your investment is only at the age between 5 to 6. Oh, the constant investment is through the whole period.
Through the whole period. That's what I'm doing. So that's why these numbers are not.
Okay.
The only numbers are the same right here.
Okay. So could you try? Could you try something like early childhood investment? Say just to give the investment at first 3 age, and then to see. But in terms of your skill production function, you do not have the dynamic complementarity part. So maybe I feel like will have not like strong impact. But you can do something like give the investment at a different age period and to see what will be sort of optimal science, like given the government can only spend the same amount of money, and how to effectively to use that money. Yeah. Cost effectively, like say, yeah. For example, what will be the best age? Yeah.
So we can do that, but people have done that, right? That's the point. It's like that's not really the point of the paper. The point is just to explain how genetic effects are. What are the mechanisms and what do they mean, and how to think about genetic influences on skill formation. But we can definitely, if we change it here, we also see effects throughout, right? Because of the complementarities, or not complementarities, because the skills stay over time. Just as a side note, because you mentioned it, we actually find substitution patterns. So the effect of investments are lower for high skilled children. So the interaction between skills and investments are negative. I never show you the translog function. It's here. So this is a translog. So basically, this is there's a negative interaction between skills and investments. But if once we do the simulations, basically the patterns are kind of very similar. So that's why we're just showing the comparables, because the message stays the same. And a lot of these interactions are kind of like, you can see they're insignificant or close to 0, right? So the PGS and the investment is like 0.04, ranging from negative to positive. And that's true for most of those parameters.
Do you know whether they will keep following those children at the primary school or like the middle school or high school?
So they do. The problem with the OSPEC is that the way it works to get access is you pay by variable, and you have to pay beforehand, and you cannot ask for more data afterwards. So we have some basic measures of skills and education on later ages, but that's it. So for example, we know whether they went to college, we know whether they grade the, what is ESG, SC.
At least like the level A task I don't know whether they have that. So one thing I'm interested in, but you guys potentially, if they have follow-up data, you can do the test is in education literature, they always say, you know, after the children at around age 8. So basically, in terms of like IQ part, like people cannot change that much. It's sort of fixed. And then like it's sort of, but maybe the thing is I want to see whether the gene part will be sort of the impact, just, you know, get weaker after, you know, age 8, or constant impact. They will not have like further things like we can change.
So we have some results in Denmark, I can tell you. So it's another paper that we're working on, Michael that is here, and Nico as well, both from the same co-authors. So where we look at the effect of genes in primary school in Denmark. So there we also observe starting grade 2, the exams, until grade 8. And we can see that this figure that we have here actually looks exactly the same once we have in Denmark, starting age 6 to 7 until age 15. We see like very similar patterns. So the effect of genes in primary school in Denmark also tends to increase. So this is just a plug for the other paper. But also what we find there is that there's a big SES difference. So especially the gap increases for both, but especially this growth for here for the 5th quintile, it's much higher for the highest for the low SES children. So they tend to catch up to the high SES counterparts, which is kind of interesting.
Okay.
Yeah. So we cannot do the aspect, the continuation of this, but we can do that with the Danish data.
I have a follow-up question on this. So with regards to the heritability increasing in ages, you're saying this continues, right? In the Danish data, at least a couple of more years. There's a point where, at least intuitively, you'd expect the genetic influence to start decreasing, right? That people kind of, you know, there's so many things that happen to them that this influence of genes would reach a peak and then maybe fall. Do you have that intuition, or do you know of any results?
So it could go both ways, right? It depends on how the shocks later in life, whether they're related to, again, to genetics or not. So if you think about that, certain individuals, they're more easily able to adjust to life shocks, and there's some people looking at that in the literature, then you would expect genetic influences to keep increasing over time. So it is the same logic from what we're seeing here, right? It's not like giving your cell level skills, genes can help you gain more skills. The same thing, like giving your cell level skills in the labor market, for example, genes can help you acquire better jobs, right? Or can help you adjust better to the shocks that you receive in the labor market. So my expectation would be that you see an increase overall effects over time, but I don't know. I don't know what the answer is. That's a good question.
What's the message then in terms of maybe policy, right? So if you're saying that this influence is increasing, at least within the horizon you see.
Maybe we can go to my last slide. So I mentioned how I see the takeaways of the paper, and then you can tell me if you disagree. Sure.
Thank you.
So the idea of the paper is to put genes into a model skill formation and try to document the importance of both parental genes and child genes for skill development. We show particularly that a lot of genetic effects are not direct, but they operate via social mechanisms. In particular, in our sample, we see that parents tend to reinforce initial difference in skills, nurture nature mechanisms. And also we see that parental genes also seem to be highly associated with skill formation in children via nature or nurture, both in terms of quantitative parental investments, but also in terms of quality, potentially via the accumulation of skills. And in particular, the takeaway for policy maybe is that these social mechanisms, which can vary across situations and can be influenced by policy, tend to reinforce genetic influences, which tend to increase over the life cycle. I guess over the earlier life, I should say, and that even when what we see is that these environmental genetic differences tends to interact to enlarge initial inequalities in skill, but that they can be changed via social behavior. I think that's kind of the message, especially the last one, is that the genetic effects operate via different mechanisms. They're not fixed, so they're both dynamic and they can be changed depending on policies and the society you live in. Okay. We still have 5 minutes. If you guys have questions, I'm happy to chat.
So yeah, I have one. So with respect to the simulation, so I understand that the main exercise here is to simply equate all the investment decisions across all the kids and across all the parents and kind of see what happens, right? But yeah. If you're, so I don't know exactly how we would do that, but if you want to kind of like plot the kind of a maximum domain in which policy might have a bite through that variable that you think might be subject to some policy, don't you need to have something on the other side, something where they're the most unequal in some sense? I don't know exactly what that would be because the investment is not bounded, I don't think, right? Or is it?
No, not in this framework.
Yeah, so in some sense, I kind of, it's hard for me to learn something quantitative from the simulation, I feel, no?
It is. It's more conceptual than quantitative. It's more about the idea, the actual numbers. But what I can show you is that we did this. Don't show because it's kind of making the same point. Suppose we had a policy that was compensating rather than reinforcing, right? So suppose if this blue line was reversed, so it went down, it was PGS. Yes. This gets flat. So this line, the blue line, gets closer to being 0. So there is a world, and that's we did this exercise before. There is a world where parents compensate enough initial differences in skills that genetic effects are just 0. You see what I'm saying? So even though genetic effects operate via these different channels and they're important because of compensating behavior of parents, we can have that association, the final association to genes and skills is actually 0. Is that what you're trying to get at, or no?
I'm not sure. I think you're telling me. I think you're telling me something about a world in which this simulation is going to look different, but it's simply a world that is not in your data. That's kind of what you're saying. So I guess. You know what? I'm having a. Maybe this is more of a presentation and not kind of a content thing. If on the one hand, your main message is to estimate the gammas, what do you learn from like dropping the equating all the gammas across all the life cycle and across all the kids? So how, I guess, I would expect something more along the lines of you take these gammas and you see what happens in a different world with the same agents or something along these lines. I don't know exactly. I guess I'm trying to say there's a tension between if your message is what the gammas are, that they're positive, how informative is it to look at what happens when they're not?
I mean, this too, yeah, I think you're getting at something that about why we're doing the exercise we're doing. So there's 2 points here. So the first one is we want to see how the gammas look like. So that's an interesting from the empirical
of course.
Like,
that period is.
Parents
I agree.
Can invest more in some children than others. So that's kind of interesting from the empirical perspective.
I agree.
You find evidence of this. Because people have posed this question, but nobody had shown before, right? So that was important. The second thing is, what does it mean? And one point we wanted to make with the paper is that this idea that genetic effects are not fixed or immutable, or the fact that genetic effects exist doesn't mean that it always would exist. or the genetic factor 0.5, it means that you always will be 0.5. It's just that the numbers can change depending on social behavior. And that's what this exercise is trying to show.
I see.
Maybe there's a better way of doing it. I don't know. But this is kind of the one we thought was the clearest. But if you have suggestions, let us know.
I would think the one way to do it is to have a functional form in which the investment is somehow bounded, and then you can kind of see the domain for which how much disparity there is among the kids based on some like initial endowment, and kind of like have that checked out for different levels of reactions from the parents.
Yeah, if you have income or expenditures in children or something, that would be a lot better, but we don't. It's a limitation of the data. Yeah, all we have is this measures of interactions that we try to compute a common factor.
So what are these interactions, for example? So they're not time, yeah. Okay.
Yeah, so it's here. The child goes to place of interest, or mom shows children picture books, or the mom and the parent reads to the child, and the father leads to the child, goes to the park. So this is kind of traditional in the literature to use this kind of measures as proxies for investments and for the quality of the home environment of the child, right? That's what we're picking up here.
So how do you actually do it? You aggregate these 23 measures of investments? And,
we can talk more about this, but there's a latent factor model. So
yeah, okay, I see. I understand.
We pose some assumptions on the structure of the latent factor.
I had a question. I think the nature of the parental investment probably depends on the changes over age. I mean, probably in the initial ages, it's more time intensive, and then later on it becomes more monetary intensive. Is there a way to control for that? I'm not sure though, but I guess there needs to be some need for that. Like especially in later education years that you talk about, like attending college and so on, they'll probably depend more so on parental income and investment of that sort, whereas these early interaction are less monetary based issues, more time intensive issues, as you suggested.
Yeah, that's a good point. That's actually something we've been trying to do, is like try to compute this, to allow basically all the functions to depend on age. So the parameters here, they're fixed, right, for all ages, but we can allow it to be different across different time periods. So we have some results based on that, and they'll be more realistic of the world to do that.
But you need to be careful in terms of identification, right? Now you want to have dynamic production function, and yeah.
I mean, I think it's identified. It's just, like Jim was saying, it can get messy very quickly, especially with the small sample size that we had initially. We don't count them.
Did you talk about?
But it's something we can think of. Yeah.
No, did you talk about how they recruited the children randomly?
Yes. So it's based on. So I think they got all. Let me get it here.
All children were
born in Avon, England, for the 91-92 cohort. That was what they were trying to catch.
Okay.
So this is like a city in England. Yeah.
Right?
But they might have missed some families. I don't know how many of the 15,000 that I have here are people that agreed to participate, or people that were initially recruited into the study.
Okay.
I don't know.
Probably one child per family, something like that. Or
yes, there are twins, but they're very few.
Oh, like multiple. I see.
There's like 100 twins.
There's some clustering stuff a little bit there. Okay, thank you.
Yeah. But it's one child per family. We know how many children there are in the family, and we see, again, for twins, we have few of them, and they're both included in the analysis. We don't separate.
All right.
But they're very few.
I mean, in biology, in medical field, this biological relationship important. So economics may be different. Yeah.
No, I think they're important too.
Yeah. Okay.
So another thing we wanted to do again is because we had this small number of children, but now we have a little bit more, is to look at birth order effects and family size and whether the investment function is different across that. But we haven't done that yet.
Okay. Thank you.
Okay.
Victor, do you know if parents who believe their kids are like candidates of geniuses relocate to like other places so that they get to enjoy their full potential, something like that?
That's a good question. So you're asking about mobility, right, among these families? I don't know. I haven't explored that. I don't know if you have like I said before to Jim, one issue with this data is that it's basically one of these very restricted data sets that you need to like buy the variables before you do the analysis. So if we didn't ask at the beginning, then we're in trouble. We cannot ask for new variables. But I should check because we ask for a lot of stuff. So maybe we ask for that. I can check.
I think you can try something like, at least in terms of simulation. For example, the children's genetic score is maybe at highest, quantile, but the parents' like a genetic score is at lowest quartile, and to do the simulation to see how that involve, and also back and forth, like sort of the children's genetic score at some kind of low level, but the parents with a good environment parents, and to see how those two type of children, like, the skill involved over time. That will give some hints in terms of, at least for the readers to know, like a different kind of family environment, how that will affect the different kinds of children. Could be interesting, like in terms of simulation results.
Yeah. That would probably depend on whether we use the translog or not, and what we allow for investment function to be different across families or not. But yes, that would be interesting. Because right now everything's kind of linear, so I don't think there's much dynamics. But we can also look at the raw data. We haven't done that. We can see.
Right, exactly. Yeah.
Okay. We're way past time, but I'm happy to stay if there are more questions. But otherwise, thank you very much for all the comments, everyone. It was great.
Thank you.
Thank you.